afternoon. So we will proceed from where we stopped in the last class to continue our discussion on evaluation of limits. So we were discussing the conditions under which a limit will exist or not exist and all of that. So we will conclude that and see how to evaluate limits, okay, based on all this background. Okay, so we have looked at one of the two of them. We said firstly, a limit will not exist if the point A, that's the point which x approaches, is a boundary point of the domain of the function, which implies that, or which tells us that whenever you have to evaluate a limit, you should have in mind a working knowledge of the domain of that function. Okay, so immediately you are able to tell the domain of the function. Now you can see that the particular point at which the limit is required is a boundary point of its domain. Then no need to work for that. The limit simply does not exist. Okay, a warning to that is, now being a boundary point, for instance, if it's a lower bound of the points, it means that there can be, there will be the limit of the function as x approaches that point from above. If it's another point with an upper bound of the domain of that function, then that means there will be the limit of that function as x approaches that number in 10 in this example from below. So as you can see it here, so in this case this function is undefined below this and it is undefined above this. It means the limit does not exist at this point. The limit does not exist at this point. That is limit, general limit. Now that doesn't mean, now as you can see here, we have said the limit is the height to which the height which a function intends to reach, okay, around a particular point. For instance, the limit of f of x as x approaches a is the height which f of x, that is the graph of f of x, okay, intends to reach around x equal to a. So that is what we're saying. So if you look at around this, now this is x equal to 0. So if you look at around x equal to 0, the height that this function intends to reach, it is height L1. So but it only intends to reach that height if you approach this value from the right. That means the only thing that exists here is the limit of f of x as x approaches 0 from above. Okay, this one exists and is equal to L1. In this case, there is no limit as it approaches from the left. So as we have seen before now, for a limit, that's the general limit to exist, the limit from the right and from the left must exist. Both of them must exist and they must be equal. In this case, one of them does not exist, so the limit as x approaches 0 does not exist, but the limit as x approaches 0 from above exists and is equal to L1. Okay, in the same vein, for the point 10, the limit as x approaches 10 from above does not exist, as you can see, because the function is undefined for anything greater than 10, but the limit as x approaches 10 from below exists, and that will be equal to L2, say. So if you say this is L2, this height is L2, okay, so the limit as x approaches 0, as x approaches 10 rather, from below is L2. Limit f of x as x approaches 10 from below is equal to L2. So quite obviously, so that is not about that. So we made example that for these functions, for instance, ln x is only defined for values of x above 0, okay, anything greater than 0. So that means the limit of this function does not exist as x approaches 0, because the function is undefined for anything below 0. You can only have limit of this function as x approaches 0 from above, for instance. Okay, so that is that about that. Alright, then we said again that another way the limit, or another situation that can occur such that the limit will not exist, or the limit of the function in consideration will not exist, is if there is a vertical asymptote. And we saw what a vertical asymptote is. Vertical asymptote is this: the fact that this is approaching, or this thing is increasing infinitely or decreasing infinitely, okay, either along the y-axis. That is why it is vertical. If it were horizontal, that will be along the x-axis. Okay, so in this case, our value, our value of this function, you know, this we said this function is, for example, f of x equal to 1 over x. So if you calculate 1 over x for values of x around 0, if those values are very close to 0 but a bit above 0, you're going to have a positive infinity. They're going to become very, very large. So you're going to have a very, very large number such that it has no limit. In this case also, you're going to have a large negative number if you're approaching from the left such that they have no limit. So just like we had it for situations when we were talking about the definition or the domain of a function, we said a function is undefined when the denominator gives us 0. Okay, that's when you have an infinite or infinity. We know infinity is not a real number, so it's the same idea here, that when you write the limit of a function as infinity or minus infinity, okay, you have actually communicated the fact that the limit of that function does not exist. So in addition to saying the limit of the function does not exist, you have said, or you have explained, that the reason the limit of that function does not exist is because the function increases infinitely as x approaches that value, in the case where it is plus infinity. Or you have said that the function decreases infinitely as x approaches that value, in the case that your limit is minus infinity. So that is what it means. So writing this way does not mean this limit exists. As a matter of fact, we have said this limit does not exist. That is what this writings actually means. So whenever you see a limit and you say the limit is equal to infinity, we have said this limit does not exist. Why? Because this function increases infinitely as x approaches this particular value. So that is what it means. So that is one of the situations you can come across. Okay, of course. So then going further, another situation where, or another condition that can make a limit not exist is when you have a break. When you have a break in the graph of that function, a break in the graph of the function. When you have a break in the graph of that function, another way to say this, or the implication of this, is that the limit of that function as x approaches a from above will not be equal to the limit of that function as x approaches a from below. That is the implication of this. And of course, we know that when this happens, it simply means the limit of that function as x approaches a does not exist. Okay, what do I mean by that? An illustration is this: you can have a function, maybe a piecewise function or otherwise. You can have a function that goes this way, so that the function behaves this way. It gets to this point, okay, and it stops. Then from here forward, the values now pick up from, let's say they pick up from here. So you now have something like this. So in this case, let's say this is x equal to a. This is where x equal to a. At this point, you will see that as x approaches a from the right, there is a limit. The limit is this height that x intends to reach, that our f of x intends to reach. Let's say it is L1. There is a limit. Okay. Again, as x approaches a from the left, there is also a limit. This is the height that it intends to reach. This is a limit, L2. So we can see that there is a limit from the right or from the left, but they are not the same because there is a break in this graph. Okay, so because of that, the limit from the right is not equal to the limit from the left, and because of that, the limit of the function does not exist. So you will be careful to observe situations like this, and where it commonly happens is when you have piecewise functions, and the point in consideration, or the point of interest, or the point that x approaches, is a particular boundary point in the definition of that function. What do I mean by that? For instance, if you have something like f of x, you have a piecewise function given like f of x. Let's say this, we'll do something like f of x is equal to, for instance, our modulus function, f of x is equal to x if x is greater than or equal to 0, and f of x is equal to minus x if x is less than 0. This is a piecewise function, so a boundary point in its definition, that is where the definition, or the point where the definition changes, okay, or where the definitions change, is what I mean by the boundary point in this context. So in this case, 0 is the boundary point, that is when you are coming from values greater than 0, there's a definition. When you are going now to values less than 0, the definition changes to minus x. So this is what I mean by the boundary point in definition. So whenever you're asked to evaluate something like this, then you should be careful to check that the limit from, so basically what you should do is to check the limit from the right first, see what it is, write it out, and also check all the limit from the left. So when you check both and they are equal, then the limit exists. When you check both and they are different, of course, nobody needs to tell you it means that the limit does not exist. What that simply means is that there is a break in the graph of that function when you plot the graph of the function. So instead of going through the stress of trying to plot the graph of the function before you can evaluate the limit, you can easily judge that from the definition of that function. Okay, so that is that about that. That is the third situation. So another situation you can come across that would mean that the limit of the function does not exist is when you have this. When you have an oscillation in the value, okay? When you have an oscillation or a sharp change or sharp changes in the value of f of x, in the values of f of x around a. So when you have a sharp change in the values of f of x around a, or you have an oscillation in the values of f of x around a. Okay, what do we mean by this? Now look at it. Instead of this oscillation, some textbooks or some people may communicate it as a violent change in the values of f of x around a. That is, it changes violently. Okay, a classical example is this. If you look at the limit of this function as x approaches 0, where our f of x is actually sine of 1 over x. So if you consider sine of 1 over x, for instance, and then you try to plot the graph of this. Let's see what we're going to get. So let's reason with what it's going to be like. You have x in this axis, we have f of x on this axis. So we're interested in the behavior of this function around 0. For instance, if you use something like 0.5, for instance, you're going to have this on sine of 1 over x, 1 divided by 1 divided by alpha x. So you can calculate. So if you look at, now we know that we are dealing with sine, so there's no, of course we are very sure there's no way sine can go above 1, and there's no way it can go below minus 1. So the sine of whatever you are doing, so this is sine 1, this is sine minus 1. So we know that this is the highest it can go, this is the lowest it can go. Okay, so you can see this is the upper bound of this function in all intervals of its definition anyways, and this is the lower bound of this. You get to understand the precise definitions of those later, but that's an English word and you should know the meaning for now. Okay, so if you carry out sine of maybe 1 over 0.1, for instance, so you calculate for 0.1, you find out what it is. It is minus 0.544. So we have minus 0.544. Let's say this is 0.1. So let's say this is 0.1 here. So we're getting the value to be minus 0.554. So we have something like this around here. If you try for, let's say 0.01, calculate 0.01, something like this. This is minus 0.5 also. So it's also minus 0.5. Minus 0.01 is 10 times less than this, so that should be somewhere around here, and it is minus 0.5. Okay, so basically if you actually check the behavior of this function around this, you're going to have something like this behavior, such that this thing it means that between this point and this point, now this thing would have gone up and down and up and down and up and down several times, okay, before it gets to this point. So you're going to have it go up and down and down and down and up and down and down. So because it's going to be oscillating between 1 and minus 1, 1 and minus 1, 1 and minus 1 around 0. You know, this thing is around 0. Imagine you have 0.5 and 1 here. Before you get to another point, you already have this thing around 0, and all of that. So it continues like that. So you're going to have it change violently. What is the implication of this? This already tells you that based on our definition of limits, we can see that f of x does not tend towards any definite height here around 0. Okay, so that is why the limit of this function as x approaches 0 does not exist. What do I mean by that? The value, we know that we cannot just put in 0. If you put in 0, you're going to have sign of infinity. That doesn't make any sense. So if you cannot put in 0. So if you put in a very small number, for instance, the way we have been checking for limits, we calculate, put in 0.001, for instance, we're going to have 0.826. If you calculate again 0.0001, calculate, it gives you 0.0357. Calculate again, put something like 0.000001, calculate, gives you minus 0.34. So it's not approaching a definite value. As a matter of fact, it changes infinitely, or it oscillates infinitely, or it oscillates violently. It goes up, goes down, goes up, goes down, violently around this x equal to 0. So because of that, the limit of this function around x equal to 0 does not exist. So that is another reason for the non-existence of a limit. So we've talked about 4 of them, and I think that is everything you can have. Those are the situations you can come across where the limit of a function will not exist and a particular value. Now it can happen that there is a hole at a point. If there is a hole in that, for instance, if you plot the graph of a particular function and it happens that the function goes this way and it gets to a particular point, it is undefined at that point, but then it continues here at the same point. Okay, let's say this is at x equal to a. Obviously this function intends to reach a definite height, whether you are coming around a, whether you are coming from the right or from the left, and that definite height it intends to reach is the limit as x approaches a. So the limit, either is going from the right or from the left, exists. So in this case there is a hole here, and that does not mean the limit does not exist. In fact, the limit exists. So for instance, you can have something like you can have a function like x squared minus 1 all over x minus 1. For instance, this function does not exist at x equal to 1, because at x equal to 1 we're going to have this to be 0 over 0. It means this function is undefined at x equal to 1. But around x equal to 1, for instance, let's enter this now function. Let's say we have alpha x all squared minus 1 divided by alpha x minus 1. So around x equal to 1, let's calculate what it will be around x equal to 1. So let's say 1.001. So let's see, it's going to give us this 2.001. Let's say calculate, still checking around this now. So we're going to have let's say 1 point, we have removed this, okay, 1.00001, for instance. Still gonna get something like this. It's still 2. If you check a number that's a bit less than that, calculate, let's say 0.999, for instance, you still give us something around 1.99. So you see that the value actually tends towards 2. And then that is the idea when we try to factorize this and say this is the difference of 2 squares. So we can write it as x plus 1 into x minus 1 and say this is also x minus 1 and have them cancel out. So, and then at the end of the day we get something like this, x plus 1. Now this x plus 1, please listen very well. This x plus 1 here is not the same thing as this function. They are not the same. Look at it. If you have a function f of x equal to x squared minus 1 all over x minus 1, and you have another function f g of x is equal to x plus 1. See, this function f of x is not the same thing as this function g of x. despite the fact that you can make a simplification and get this. Now, what is the difference between this and this? The difference between this and this is that this particular function is defined at x equal to 1. If you put x equal to 1 here, you're going to get 2. Whereas this one is undefined at x equal to 1. It's going to give you 0 over 0. It is undefined at x equal to 1. So at x equal to 1, it has no value. So it is as simple as that. That is the difference between them. So you should know that these two are different. So, you know, when factorizing or when doing something like this, when we're dealing with proof of limit, I'll always attach a condition that provided that a particular thing we are cancelling out will not result in 0 over 0. If you can remember. If you can't remember, you can still watch those previous videos again and see them. For instance, while you are cancelling this out, you are currently where this thing is allowed, or this function, for instance, x squared minus 1 all over x minus 1 will be equal to, is the same thing as x plus 1, provided that x is not equal to 1. Because if x is equal to 1, this will be 0 over 0, and you can't cancel 0. 0 and 0 cannot cancel. Okay, that does not make any sense. So this thing is only reasonable and correct when x is not equal to 1. Okay, and because we are dealing with limits, we know that we just want the value to approach 1. Okay, it does not have to become 1. That is why our simplification here, or just substituting x equal to 1 in this function, will give us the limit of this function as x approaches 1. Because we are dealing with limits, it means that the function we are trying to use to replace this may not be defined at that particular point which we are interested in. So it may be equivalent, or it should be equivalent to the original function at every other point except or possibly except that particular point we are dealing with. So that is the idea with all of these things. So have it in mind, or bear it in mind, they are not the same functions. Okay, so then I guess that is that about that. So that's that. So we can say in this case, for instance, we can say this one is a generalization of this one, because this one makes this function, it makes the function f of x to be defined at all points, including at x equal to 1, when you have it redefined this way. But just know that these two are different functions. Alright, so that is that about that. So having a hole in the graph of a function at a particular point does not mean the limit does not exist at that point. Okay, the limit will exist if the function approaches a definite value, okay, or it tends to a definite height around x equal to a. So that is the only thing. So that is, if it tends to the same height, whether you're coming from the right or from the left, then that height to which it tends is the limit, okay, as x approaches a. So that's that about that. Right, so you now understand all of this. So it's a good thing to do. So we can now move on to begin to evaluate limits. So we'll now begin to talk about evaluation of limits. We look at different methods of evaluating limits. Evaluation of limits. So the first method, which is the simplest method, which is the first one you should know, is the substitution method, when you're trying to make a substitution. So in the case of the substitution method, we're trying to make a direct substitution. Now this works when you have a polynomial expression, okay, you have a rational function. You can remember what the rational function is. When you have polynomial at the numerator, polynomial at the denominator, a rational function, that's what it is. So when you have something like that, then the substitution method works fine. You can just make a substitution and get your result. Okay, so reason for that, as we'll get to see later, is because the polynomial function is continuous. When you have a polynomial function, when you have a rational function, it is continuous, provided that you don't have your, what is it now, you don't have your function to be undefined at that particular point we're interested in, but that's not the point anyways. So what are we really saying? When you have a polynomial, okay, you can always, or you should always, use direct substitution. It is called direct substitution method. Okay, you understand what I mean? Now when you have a rational function, okay, so when you have a rational function, also use a direct substitution, and that will be correct provided that it does not result, or it does not give you 0 over 0. Okay, if it doesn't give you 0 over 0, you are good to go. Okay, this is useful obviously for situations where you have x to be approaching a, where a is a finite number, a is some real number. So you can always use this approach. Just make a direct substitution and you are good to go. Okay, so provided for the rational function you don't get 0 over 0, then you are correct. If you get something like a, maybe you get a real number divided by 0, obviously you know what this means. This is infinity. It means the limit does not exist. Okay, that is what it means. Okay, so but when it results in 0 over 0, we simply cannot reach a conclusion on what the limit of that function is yet at that particular point. So what we do is to subject it to other methods of simplification and see what it really gives us, and see if we can actually determine it using other approaches. So the substitution method is indeterminate when it results in 0 over 0. When you get 0 over 0 by simply slotting in the value that x is approaching. So that is that about that. So let's look at some examples. For instance, if you're asked to get the limit of, let's say you can think of any polynomial. Let's say you have x squared plus 2x minus 1. Limit of this as x approaches 2, it is simply equal to, you just make a direct substitution of x equal to 2. This is a polynomial. That is why we are doing this. Please don't forget. It is because it is a polynomial, and the reason for this is because a polynomial is continuous. So a polynomial will not have a break at any point. It is continuous. So the value it's approaching is the same thing as the value of that function at this particular point. So when you substitute here, you're going to get your result just to 2 squared plus 2 into 2 minus 1. This is 4 plus 4, 8 minus 1, which is 7. Very straightforward. This is the limit of this function as x approaches 2. Okay, this is quite easy. And then it happens that you may never have come across anything like that. So then it then becomes something else when you get to the exam or something. You may not be able to get something like this, something as simple as this in your questions. So but then it's good that you know it, that you can do a direct substitution. Okay, so again, look at this example. If you are asked to get the limit of x cubed minus 8 all over x plus 2, okay, as x approaches 1, what should be your first reaction? Your first reaction is to make a direct substitution. So directly substitute. You're going to have 1 raised to power 3 minus 8 all over 1 plus 2. So this is going to be what? This is going to be 1 raised to power 3 is 1 minus 8 divided by 1 plus 2, which is 3. 3. So you have 1 minus 8, which is minus 7 over 3. And that is the limit of this function as x approaches 1. So it's quite easy. So when you have a rational function, a polynomial function, the first thing that should come to your mind is direct substitution. Why don't you have to worry about the domain of the function first? Polynomial functions, polynomial functions are rational functions. So you know, rational means it has a polynomial here and it has a polynomial here. It's always defined, or it's defined for all real values of x. So the condition of saying the that the point of interest may be a boundary point in its domain can never even happen, because there's no point that will be a boundary point in its domain. So that is why we can always do something like this. For a polynomial is always defined as all real numbers. For a rational expression, you can easily tell when it is undefined. It is undefined when the denominator is 0, and then if the denominator gives you 0 and the numerator is not 0, you already know that the limit does not exist. You can just write that the limit is equal to infinity. That's to communicate that the limit does not exist, because the function increases or decreases infinitely as x approaches that particular value, so it's fine. But if it happens that the numerator gives you 0 and the denominator also gives you 0, then you know that we cannot reach a conclusion from the results. In layman terms, we say that the limit is indeterminate at that point. So that is that about that. For instance, if I have something like the limit of x cubed minus 8 all over x minus 1 as x approaches 1, for instance, when I make a direct substitution, that should be my first reaction, making a direct substitution. So when I make a direct substitution, I'm going to have 1 raised to the power 3 minus 8 all over 1 minus 1. Obviously, this is going to be minus 7 all over 0, okay, which is equal to minus infinity. It is fine. We are saying this limit does not exist. Now, for all situations like this, it usually happens that the limit can be minus infinity or plus infinity most times. When you have a limit to be plus infinity, I said most times, not all of the times. When you are dealing with rational functions like this, when you have the limit to be minus infinity, it also implies that it could be actually plus infinity. Okay, what do I mean by that? If you check this function out, for instance, on a calculator, you have something like alpha x raised to power 3 minus 8 divided by alpha x minus 1. I will find out, for instance, the value that this function approaches as x approaches 1. So let's say we are checking the value as x approaches 1 from above. We're going to have 1.00001, for instance. We check. It's giving us a large negative number, which is minus infinity, or which means or implies minus infinity, as we have seen. Or you can still check further and put minus and put something like 1.000000001. It's going to give you a larger number, so the number keeps decreasing infinitely. Why am I saying decreasing? Because it's a negative number. So then if you calculate using a number that is lower than or less than 1, for instance, you're going to have something like, let's say 0. What do you call it now? 0.999. Let's say we use 0.999, for instance, and calculate. You see, it gives us a positive large number. So when you do another one, for instance, 0.999999, for instance, gives us another positive large number. So it can actually be plus infinity or minus infinity. As a matter of fact, most of the methods we will learn, or most of the methods we will adopt here, has or have an implicit bias for limits as x approaches that value from above. So most times it's just smart to even check what it would be if we actually did it. You can check with a calculator if you actually did it from below, because there is a direct, or let's say an unwritten bias for our method to actually evaluate limit from above instead of it being from both. Instead of it actually working from both from above and below. For instance, what we have done now simply told us that the limit is minus infinity, whereas the limit could be actually plus infinity or minus infinity. That is to tell you something that whenever you come across this infinity as a result for limit of rational functions, it actually is telling you that, again, it is pressing home the idea that the limit does not exist, because the limit can actually be written as plus infinity or minus infinity, again depending on how you see it. It is basically to tell you that in the case of these irrational functions, it tells you that if you approach from above, it is that number or that result that you got. If you approach from below, it will just be opposite of that. So this is tell you that this limit does not exist, and the reason it doesn't exist is that for values of x above 1, the function decreases infinitely, and for values of x below 1, the function increases infinitely. So basically, the limit from above and from below, they are not the same. And even aside that, the fact that they are not real numbers makes it non-existent. So that is that about that. Okay, so now what then happens? What if you have a situation like this? Maybe you are interested in the limit as x approaches 2 of x raised to power 3 minus 8 all over x minus 2. If we have something like this, our first reaction should be a direct substitution. So I'll make a direct substitution and say this is 2 raised to power 3 minus 8 divided by 2 minus 2. So this is what? 2 raised to power 3 is 8. 8 minus 8 is 0. And then 2 minus 2 is 0. So you have 0 over 0. So we say that what this is indeterminate. Indeterminate means that indeterminate does not mean it does not exist. It simply means we cannot tell from this approach we have taken. So then indeterminate is not the end of the solution. We will have to check further using other methods of simplifying or evaluating limits to check if the limit actually really exists, and we can tell what exactly it is. So but for now we are saying we cannot tell what this is. So that is that about that. An interesting thing about this is that it is also equivalent, as you get to see later, to infinity over infinity. For instance, I can write this x raised to power 3 minus 8 all over x minus 2. For instance, I can say this is the same thing as 1 over x minus 2 divided by 1 over x cubed minus 8. Do you agree with this? 1 over x minus 2 divided by this is the same thing as writing 1 over x minus 2 multiplied by the inverse of this, which is x cubed minus 8 all over 1. So from here you are going to have x cubed minus 8 all over x minus 2. So they are equivalent, okay, functions. So if you make a direct substitution this way, you know what you're going to get, right? You're going to have something like 1 over 0 divided by 1 over 0. I hope you understand what I'm doing. When you substitute 2 here, you're going to have 1 over 0 divided by 1 over 0. Basically, this is going to be infinity over infinity. And then that is why we say this is also indeterminate. We cannot tell what it is. For now, we cannot tell what it is. Now, why is this so? We know infinity is a large number. Normally you will feel that, okay, we have a very large number, we have another very large number, why can't we just cancel them out? No, the reason is large is relative. Large is not a specific mathematical word. For instance, if you are dealing with let us say time, for instance, if I want to switch on a bulb and I then press the switch, bam, I expect the bulb to come on immediately. Based on my own smartness or intelligence as a human, for me, I feel that immediately I punch or I press the switch, the light comes on immediately. That is what it feels to me. But actually, if you have an accurate time measuring instrument, you will see that it does not come on immediately. There is actually a time interval between when you punch the switch and when the light comes on. Maybe that's something like maybe 50 or maybe 50 microsecond or 5 microsecond or something, or nanosecond, something like that. Okay, now in that situation, if it happens that I punch my switch, I press the switch, bam, and the light takes like, let's say, 2 3 seconds before it comes on, I'll be worried. I'll feel like this is taking a very long time, because based on the normal range I expected, or the normal time I expected to come on, okay, this is outrageous. This time is outrageous compared to the normal interval it should take, which should naturally be non-detectable for me. Okay, now when it becomes detectable for me, I'm worried, because this is taking unnecessarily long. So you get now. So it's just like your mom at home, or what is Yoruba people, when they send you on errand. They send you on errand from morning, and you go. They send you to go and buy me akara or at the junction there, and you now go from that time. Maybe they send you from 9 a.m. and they've already prepared the custard or ghee or whatever you call it that they want to use to eat that morning akara now. Then you go from 9 a.m. Maybe you get there is queue, you now wait for your turn, or maybe it's very hot at the hot and everybody likes it, so you have to wait for your turn, and you're just there, you are there till, let's say, 10 a.m. That's 1 hour already. Then you are getting back home. Let's say you got back to your house like 10:20 a.m. Your mom will be like, so they are shouting at you. Now what has happened in that case? Now you have just taken 1 hour 20 minutes. 1 hour 20 minutes in some context will be a very short time. For instance, if you go for tutorial, if you attend Max tutorial in the evening, you know that normally our classes will go for 2 hours. If you now go for the class and we spend just 1 hour 20 minutes, it will feel like this thing is too fast now. Why are we ending class so quickly? Because this is not the usual range it is. Okay, so that is what we mean by infinity. Like we are taking so long, like Lord, like that. Okay, it is because of the context. The context determines whether it is infinite or not. So in some context, for instance, 1 can be infinity if we are dealing with values, or we are working with a system where the expected values are around maybe 0.0005. Maybe they are in the nano range. Maybe we are looking at something like 1 nanosecond or 2 nanoseconds, and something now happens. You record it and you now find 1 second. You now be what is happening? That for that context, for that situation, for that kind of analysis, 1 is infinity. So that's why I'm saying that infinity over infinity is indeterminate, because we don't know what exactly this infinity is tending towards to, how fast this one approaches infinity compared to this one. Okay, now what do I mean by that? If you look at 1 over 1 over x minus 2. If you check 1 over x minus 2, 1 divided by alpha x minus 2, and you find out, for instance, let's say we want to find out what this will be when we are on maybe 0.001. This is tending towards 0. When this thing is it's tending towards 2, it's tending towards 2. Let's check something like 2.001. When this thing is at 2.001, this one is at 1000. Now let's check the other one. 1 over x cubed minus 8. Look at it, x raised to power 3 minus 8. So let's check what it will be at 2.001. At 2.001, this one is still in 83, whereas this one has gotten to 1000. So you see that infinity of this one is talking about something like 1000, whereas this one is talking about something like 82.3 at a particular stage. So it means that if you go further, for instance, if you go further to 2.0001, for instance, we check 2.00001, for instance, and check, this one is around 8333. That is the infinity in this context. If you check for 1 over x minus 2, you see delete 1 over x minus 2. If you check, calculate for this value, you're going to see this one is already at 100,000, whereas that one is something like 8,333. So it tells you that the infinity here, okay, it means that this thing may be approaching infinity faster than this one does, or this may be approaching infinity faster than this one does. That is why we cannot tell what infinity over infinity is because they are not, the two of them are not approaching infinity at the same rate. So then at every instance when we divide them, we cannot tell what exactly the result will be. That is why we say it is indeterminate. It is the same idea with this 0 over 0. We don't know how far or how well or how close this gets to 0 when x is approaching 2, compared to how close this gets to 0 when x is approaching 2. What do I mean by that? If we check this, if you check how far x raised to power 3 minus 8, find out what it is when x is approaching 2. Let's say when x is this value. So you see this one is already 1.2 times 10 raised to power minus 4. If you now check for the other one, x minus 2, when x is approaching this value. So check for x minus 2. Don't forget that one is 1.2 times 10 raised to power minus 4. So x minus 2, let's calculate what x minus 2 will be. This one is on 1 times 10 raised to power minus 5. So you can see that the zero that the rate at which this one is approaching 0 is different from the rate at which this one is approaching 0. That is why we are saying this 0 over 0, the way it is here, because we are dealing with limits, is actually indeterminate. We cannot tell exactly how fast this one approaches 0 compared to how this one approaches 0. Okay, we cannot tell how well or how fast this one approaches infinity, this one approaches infinity compared to how this one approaches infinity. So that is what this indeterminate means. We cannot tell for now. Okay, so that means we will need to look at other ways of actually comparing or trying to visualize what is happening, or the rate at which one approaches infinity relative to the other. So that is the idea. So this is one method, and this is what you should always use. This is what you should always come to your mind when you have a non-piecewise. You know, all these functions are non-piecewise functions. Non-piecewise functions that are in polynomial or rational forms. Okay, so that's that about that. You know that what's it now? There are algebraic functions. We talk about algebraic functions, something like square root of x, okay, minus 1, for instance. Now you should not just use direct substitution. You know that these examples are carefully selected. When you are dealing with something like this now, direct substitution should not be the first thing that comes to your mind. The first thing that comes to your mind is, what is the domain of this function? Is the value x is approaching a boundary point of the domain? If it's a boundary point of the domain, see, don't disturb yourself. No substitution can save you from getting the wrong answer if that's what you do first in that case. So you just say okay, yes or no, because it is a boundary point, the limit does not exist. See, just leave it, go away. If you have something like ln x, for instance, that is a what do you call that? That is a transcendental function. Okay, they are different from these ones we have been talking about now. So if you have something like sin x, for instance, if you have sine, if you have sine, you have cosine, you have tan, you have tan, and all of that, what should come to your mind first is, what is the domain of this function? If you cannot figure out, maybe it's complex, then you can actually use some other approaches. You can try to use direct substitution and see, okay, what exactly is this, and then find out the behavior of that function around that number to be able to reach a conclusion. But we will get there. So I believe you understand this already. So this is the idea with all of these approaches. Okay, now, so that is that about that. So we can now move on to something else. Okay, so what method can we use when we come across an indeterminate form? So whenever you come across an indeterminate form with a rational function like this, the first thing that should come to your mind is what we call the factorization method. That is the next method. This is the first method, direct substitution method. Next one is factorization method. So you say if the functions can be factored, if they can be factored such that maybe the one at the numerator, of course, we cancel out the one at the denominator. So when that is possible, then you are good to go. It will help you clear off the indeterminate form. You should resort to this only when you have the indeterminate form already. So now look at an example. An example is this limit we are dealing with, limit of x cubed minus 8 all over x minus 2, as x approaches 2. So what is the idea in the factorization thing? For instance, when you factorize this, you know how to factorize this. You can divide this by this, for instance, and see how that pans out. For instance, you do this is x minus 2. You should know it offhand, but if you don't know it offhand, there is no big deal. X cubed minus 8. X in this is x squared. So x in this x cubed minus 2x squared. Okay, subtract, this goes to 0, then you have 2x squared minus 8. Then x in this is 2x, so you have plus 2x. X in this is going to give you 2x squared minus 4x. That is when you multiply this and this. So when you subtract this, we cancel this. So at the end of the day, you have 4x minus 8. So you have x in this is 4, so you have plus 4. 4 multiplied by this is 4x, multiplied by 2 minus 2 is minus 8. So that's the end of it. So this tells you that you can divide this by this and get this. So it means I can write this function x cubed minus 8 all over x minus 2. I can write it as the product of x minus 2 all over x squared plus 2x plus 4 divided by x minus 2. Yes, the two of them are equal, they are the same. Let me write it here so I will continue together here. We have said that if you have limit as x approaches 2 of x cubed minus 8 all over x minus 2, okay, I've said this can be simplified or factorized. We can factorize the numerator function and say this is going to be equal to x minus 2 multiplied by x squared plus 2x plus 4, then divided by x minus 2. Now this is fine because this function is the same thing as this function. Now why we can cancel them out is because this is equal to x squared plus 2x plus 4, okay, all over x minus 2. I'm saying that this x cubed minus 8 all over x minus 2 is equal to this, okay, and this can cancel this out provided that x is not equal to 2. Why? Because if x is equal to 2, this will be 0 and 0. 0 and 0 cannot cancel out. And why is this simplification correct? Because we are interested in the value or the behavior of this function around 2. We are not interested in its behavior at x equal to 2. We are not interested in that. We are just interested in what it is or the value that the function approaches or tends to, the height that it tends to reach around 2. So that is why this thing is correct, and that is why we can use this simplification. So because of that, we say that the limit, okay, as x approaches 2, okay, of x cubed minus 8 all over x minus 2 is simply equal to the limit, okay, as x approaches 2 of this polynomial, which is x squared plus 2x plus 4. So we are good to go. So we now have a polynomial now. So this is just going to be equal to, by direct substitution, 2 squared plus 2 into 2 then plus 4. So that is going to give us what now? This is going to give us 4 plus 4 plus 4. So that is going to give us 12. So that is the limits of this function as x approaches 2, either from above or from below. So you can check that and verify it with a calculator. So that is that about that. It's quite easy. So you can always use this factorization method, okay. So having 0 over 0 and infinity over infinity is to actually drive home this situation or this discussion we had here, that it can happen that the function is undefined at that point. That is, it can happen that the function as a whole at this point. So having 0 over 0 is to tell you that this function is undefined at this point. So there is a hole there. So, but then despite that, when you are coming from the right, when you are coming from the left, the function approaches the same value. Okay, that is what usually happens when you have rational functions like this. So that is what we have tried to communicate there. So if you try to plot the graph of this, you see that for values of x around 2, you're always going to get something very close to 12. Alright, so that is actually the idea with evaluating the limit of a function using calculator. So that is the way it works. So then I guess that is that about that. Alright, so I'm going to give you some assignment questions on this so you understand. Try your hands on them and see how it goes. Right, so we move to another method that we can use to simplify or to evaluate limits. Method 3. It is called the how do we call this now? Let's say rationalizing the denominator will not make sense. We can call it the conjugate method or use of conjugate method. Can you remember what the conjugate is? Can you remember what the conjugate is when you dealt with sorts in 100 level? Okay, so this is usually used when you have a an algebraic function, involving roots. Okay, you can remember that if you have roots 2 or root x, for instance, the conjugate of root x is simply root x. If you have something like root x plus 2, its conjugate is root x minus 2. So we can use this idea, okay, to actually get the limits of some functions, okay, under some condition, under the condition when it is indeterminate. Okay, the one we first looked at now, the factorization method, okay, will mostly work for situations where you have rational functions. Okay, this is an algebraic function, for instance. Okay, so let's take some example. You understand what I'm trying to say. For instance, if you evaluate, let us say you have something like this. If you have something like limit as x approaches 5 of square root of x plus 11, okay, minus 4 divided by x minus 5. So in this case, we know the domain of this function. This function will be undefined, firstly at x equal to 5. So x equal to 5 is excluded because that will give us 0 here. But then that does not disturb the limit as x approaches 5, because we really are not interested in the value of the function at x equal to 5. So that one is out of it. Then when you have the numerator, we know that the square root, what we have under the square root cannot be negative. So when you have this to be 0, that's the lowest we can go. If you have this to be 0, then x will be minus 11. So x cannot go below minus 11, because that will mean what we have here will become negative. Okay, so basically the domain of this function, if I'm interested in the domain of the function, will be something from anything from minus 11 forward. Okay, then it will get to 5, but it cannot include 5, so we have comma 5. Then in addition to going from 5 forward to any real positive number, so we're going to have something like this. This is the domain of this function. Obviously 5 is not a boundary point in the domain. Okay, it appears like it's a boundary point, no, but that's not what we mean by it being a boundary point. It means to be a boundary point if the function is not defined for values before and for values after, or for values after. In this case, we have it defined for values before and values after for 5. So 5 is not a boundary point for this domain. It just happens that it is a point where there is a hole in the function or in the graph of that function. So going further now, we know we can take a direct substitution. We are sure that the numbers around 5 that we want to study are actually in the domain of this function. So because of that, we can actually do a direct substitution and see what it gives us. Why didn't we have to do all of this for this situation? Because we know that these are both polynomials, and polynomials are really defined for all values of x, all real numbers. So the only situation where this is undefined is at x equal to 2, which does not affect our analysis, because we are not interested in its value at x equal to 2. We are just interested in its value as x approaches 2. So that's why we didn't have to worry much about that here. But in this case, you can just do a simple, thinking through what the domain of this function will be. So that's what we have done here to be sure that the values of x around 5, which we want to study, are actually, x is actually the function is actually defined for values of x around 5. Around 5 is a relative thing. It could be maybe 0.1 below and above. It doesn't make any. It can be even be 0.001 below and above. It is still defined around 5. So that is what it is. So now we can make a direct substitution and check what it gives us. So we can check. This is going to be square root of 5 plus 11 minus 4 divided by 5 minus 5. So this is going to be 5 plus 11 is 16. So I have square root of 16 minus 4 all over 5 minus 5. Square root of 16 is 4. Of course, this will always take the positive value. So 4 minus 4 is 0 and 5 minus 5 is 0. So this is evidently indeterminate from a direct substitution approach. So then we will look at another way of seeing how each one of them increases as x approaches 5. So to do that, we will multiply top and bottom by the conjugate of the numerator. Which one are we sure of which one to use whenever we come across a situation like this? Are we to use that of the numerator or that of the denominator? If it happens that only the numerator, as in this case, has this such sodic expression, we will only multiply top and bottom by the conjugate of the numerator. If it happens that they both have it, and of course you have a situation like this, you will multiply top and bottom by the conjugate of the numerator, then also by the conjugate of the denominator. You do all of that together. Okay, now it may even happen that you have a situation like this. Okay, we get to see it. For instance, if you have x approaching infinity and it gives something like infinity minus infinity or any other indeterminate form that we get to know, this also can help you out. You can multiply top and bottom by the conjugate of any of them that appears in sodic form and see what actually comes out of that. Alright, so now going forward, I can now write that square root of x plus 11 minus 4 divided by x minus 5 is actually equal to square root of x plus 11 plus 4. That will be the conjugate of this. It is this relation that will change, divided by square root of x plus 11 plus 4. We are multiplying top and bottom, then multiply by square root of x plus 11 minus 4 divided by x minus 5. And why is this possible? I told you we cannot multiply by 0 over 0, we cannot divide by 0 over 0, so because that will be indeterminate. This is possible, or this is feasible, provided that this will not give us 0 and this will not give us 0, okay, which is fine. Okay, so that is provided that this thing here is not 0 and this thing here is not 0. Okay, so we know that this cannot give us 0 because this one already gives us 0. This one is 0. We are very sure of that. That's what we have already checked. So we know that root of x plus 1, root of x plus 11 plus 4 will not be 0 around this value that we are dealing with. Okay, for this to be 0, you are going to have this square root to be equal to minus 4, which is not possible. So that is why we can do this thing here. I've told you before, you can multiply top and bottom by the same value and have the result to be equivalent to having this alone. It has to be that number you're multiplying top and bottom with cannot be 0. It has no possibility of becoming 0 in the interval or domain of consideration. Okay, so that is satisfied here. So then we can proceed to simplify this. So we say this is equal to, when you multiply this and this, you can see this is difference of two squares. This is like you have a plus b multiplied by a minus b. So that's going to be equal to a square minus b square. So what we have here is simply square root of x plus 11 all squared minus 4, which is b all squared, and divided by what we have here, which is just square root of x plus 11, okay, plus 4. Okay, we have this, then multiply by this one, which is x minus 5. So this is what we're going to get from this. So this is going to give us, when you square this, you're going to have x plus 11, because the square root sign goes, then minus 4 square, which is 16, then divided by square root of x plus 11 plus 4, okay, then multiply by x minus 5. So that is that about that. So that is what you get from this analysis when you have taken the multiplication. So now from here we can simplify further. This is going to give us x plus 11 minus 16. That's going to be x minus 5. You see that? Then this divided by square root of x plus 11, okay, plus 4, then multiply by x minus 5. So we have x minus, if you put in 5 here, you know, you're still going to get 0 over 0. So this x minus 5 can cancel this x minus 5. Okay, so this can cancel this, provided that x is not equal to 5. Of course, we are safe because we are not interested in x becoming 5 in the first place. Okay, so we can have this. So that means, provided our x is not equal to 5, this function is equivalent to this function. That is what we have tried to show with all of these things. That is why what we have done here is correct. Okay, so because of that, I can now write that the limit, therefore the limit of x plus 11 square root of x plus 11 minus 4 divided by x minus 5 as x approaches 5 is actually equal to the limit of 1 over that we got in just now, square root of x plus 11 plus 4. So that's what we obtained here as x approaches 5. Okay, you see that? That's what we obtained here. Right. So then we'll go further to say, now we can use the direct substitution and see what the behavior of this is. Okay, so using the direct substitution, this will be equal to 1 divided by square root of 5 plus 11 and plus 4. Square root of 5 plus 11 is square root of 16, which is 4. 4 plus 4 is 8. Therefore, the limit is 1 divided by 8. Answer. So that is the limit of the function that we seek. So that is that about that. Right. So I believe you understand this perfectly. So if you do all of these things, for instance, if you have a function like this and you've tried all these methods and they don't work, that probably means that it is not a rational function and it is not an algebraic function. Probably is a transcendental function. Then there are a lot of other ways we can deal with those transcendental functions, depending on the behavior of those functions. All right. So that is that about that. So we can have other kinds of limits we want to deal with and see what it is going to give us and see how we can get those limits. I think we should move on from here in the next class. You're going to see how we can evaluate limits under different other conditions. For instance, if you have limit approaching infinity, okay, and then maybe at the end of the day you get your indeterminate form to be infinity over infinity, okay, how can you work around that? Okay, how can you evaluate limits at infinity? Then we also look at some special limits. You should have known those before, like limit of sine x over x as x approaches 0, p equal to 1, and others like that. So we look at it, then I think from there we'll be fine. So L'Hospital's rule. I should like to talk about L'Hospital's rule and some other indeterminate form, but it appears to be more appropriate for discussion when we have first discussed differentiability of function. Anyways, I will see how best it should be presented, and if we should do it as it is done in the school, it was done in the school lectures before differentiability of functions, we will, otherwise we'll postpone it. Alright, so I believe you got this. So I'm going to give you some assignments on this, so you try your hands on them. I'll put it on the group right away. Alright, thank you for your interest in Max Engineering tutorials. Continue to stay safe. Please do us or do me a favor, do your friends a favor too. If you have friends that actually need these classes, probably they are waiting for us to resume first before they join us, please let them know the danger in their waiting. You can see that all that we have been doing so far are stuff for topics and sections already discussed before the lockdown. Imagine we have to rush through all of this when we have resumed, and we have maybe like just 4 weeks to the mid-semester test. They're going to take off from where we left off, so it's going to be very, very devastating, because it will be almost impossible for me to even calm down and begin to explain this way, because we will not have the time at all. The reason I'm doing all of these things quite elaborately and one after the other like this is because we actually have the time, because everyone is in a relaxed mood at home, so it's fine. All these things we have been doing for over 4 weeks now. I think this is the 5th week. We did like double of these or even triple of these within 2 weeks in the regular classes, so you can imagine what it is like. So please inform your friends, let them know that it is best they join us now. Let them know how effective it has been, and it's best they partake now, so that when we resume we can all flow together. All right, thank you very much. Continue to stay safe.